Up till now, we have practiced about the torsion formula. We are able to calculate the torque in the solid shaft and the hollow shaft. We know that the torsion strength is given as shear stress multiplied by J divided by R. Here the strength is dependent on the geometric property that equal to J. And if the value of the J will be higher, naturally the strength will be higher. At the same time, you have to also think that what is about the weight, because weight means cost. If it has a higher weight, then it has a higher cost. So people are interested in a tubular shaft rather than the solid shaft if the length of the shaft is very large. Say for example, in the case of propeller system, that is, we have a car engine is shown here. So this one is the engine here. We have a transaxle and we have central differential. We have a front wheel and the rear wheel. When the power is transmitted from the engine to the rear wheel, they require a rear differential. And the power is transmitted from engine to the rear differential by a hollow shaft. Because the length is very large, and if the length is very large, then we require here very large volume of the material of the shaft. Therefore, instead of using the solid shaft from the engine to the rear differential, we'll use here a hollow shaft. For same power transmitted, the cross-sectional area required for the hollow shaft will be smaller as compared to solid shaft, and that is the net saving in the material. And therefore, our point of interest now is a comparison of the solid and the tubular shaft, that is a hollow shaft, in point of view to the strength, to the weight, where strength is defined as the torque T, that is a torque carrying capacity, which one is defined as the shear stress multiplied by polar moment of inertia divided by outer radius. We know that the shear stress is maximum at the outer radius. As far as the weight is considered, weight is simply given as a product of density multiplied by G, that is the acceleration due to gravity multiplied by cross-section area multiplied by length. So what we are interested here, that the strength to weight should be the higher value. And that is possible in the case of hollow shaft as compared to solid shaft. This is exactly we want to prove in this video. So strength to the weight advantage of a tubular shaft relative to the solid shaft is the reason that they are frequently used as a torsion members in many applications, such as a drive shaft of vehicle, say for example trucks. So normally if the length is very large, in that case you can prefer the hollow shaft. Whereas for smaller length, you can prefer the solid shaft. The weight of the solid shaft will be more as compared to the hollow shaft for the same power transmission, that is the same value of torque. As far as the solid shaft is considered, that is the value of the shear stress at the center will be 0, and this value will go on increasing and is the maximum value. We have radius R equal to capital R. So the distribution is linear over the entire cross section. So the shear stress in a solid circular bar are maximum at the outer boundary of a cross section and is 0 at the center. Therefore, most of the material in the solid shaft is stressed significantly below the maximum shear. So here if I want to show you the average value of the shear stress, the average value of the shear stress will be tau max plus 0 divided by 2 over the radius equal to R. Approximately I will show you this value, and this value of tau average is exactly equal to tau max divided by 2. Maximum value of the shear stress will occupy almost here in the outer boundary. That advantage was taken in the case of tubular shaft. In the case of tubular shaft, we have inner radius is R1, outer radius is R2, and we have thickness is T, and the distribution is only from R1 to R2, and the maximum value will occur at radius equal to R2. So at R is equal to R2, we have maximum value of tau max, and this value is much larger as compared to the 0 value at the center in the case of solid shaft, and therefore the average distribution, you will say the average distribution is much larger in the case of hollow shaft as compared to the solid shaft. So in a hollow tube, most of the material is near the outer boundary of a cross section where both the shear stress and the moment arm is higher. Here the moment arm will be R1, here the moment arm will be R2, and this moment arm is variable. Whereas the distribution of a shear stress here is only from R1 to R2. So for any shear stress you consider here, the value of the moment arm, that is the distance from the center, will be very high. So this is the advantage. And secondly, the average distribution of a shear stress in the case of hollow is much higher as compared to the solid. So I have taken here same cross section, and this distribution is linear. So distribution is from 0 to maximum. Therefore, smaller value of the arm and the smaller value of the shear. Whereas in the case of hollow, we have larger value of the arm as well as we have larger value of the shear stress also. This one is the advantage in the case of hollow shaft. So to transfer the same torque, we require the less material in the hollow shaft as compared to the solid shaft. Hence, for long shaft, we should always select the hollow shaft as compared to the solid shaft. Thus, if we are keeping in mind the weight reduction and the saving of material are important for us, then it is always advisable to use the hollow shaft. If you are using the hollow shaft, you have to take care that the thickness T, because buckling may be the problem in the case of long shaft as we have seen in a propeller. So that buckling has to be avoided due to the self-weight. To avoid the buckling here, the value of the R2 divided by the maximum value of the T max should be have to keep minimum equal to 12. If you have lower value than 12, then the buckling may be chances or the wrinkling may be chances. So when designing a shaft, R2 by maximum thickness must be greater than equal to 12 to avoid the buckling or the wrinkling of the wall of a tube. So whenever you have to find out the weight is basically given as rho. So we are using the same material for solid and hollow. The rho will be same. Even the acceleration due to gravity is also same, multiplied by cross section area equal to A multiplied by length L. Since we have to replace the solid shaft by hollow shaft, the length is also remains same. It means that our weight is directly proportional to area. And in the case of hollow shaft, the cross section area is R2 square minus R1 square, that is the outer radius square minus inner radius square. And in the case of solid shaft, it is simply pi r square. Pi and pi will be get cancelled. So we can very well calculate here what is the ratio of the weight of hollow cylinder to the solid cylinder is simply R2 square minus R1 square divided by capital R square, where R2 and R1 outer and the inner radius for hollow shaft and capital R is the radius of the solid shaft. So our objective here is to prove that the hollow shaft has a light weight as compared to the solid shaft for the same power transmission. So to prove this, I will take here one sample numerical. A steel shaft is to be manufactured either as a solid circular bar or as a circular tube. Shaft is required to transmit a torque of 1200 Newton meter for both, that is solid shaft as well as for hollow shaft, without exceeding an allowable shear stress of 40 megapascal nor an allowable rate of twist of 0.75 degree per meter, and the shear modulus of elasticity is 78 gigapascal. So for designing the solid and hollow, we have two constraints. One constraint is the shear stress should not be exceed than 40. So for that purpose we'll get one diameter for the hollow and one diameter, that is DO and DI, for the hollow section, and one diameter we'll get for solid section. Then second constraint we have the twist, that is theta by L is 0.75 degree per meter. So using this constraint we'll get another set of diameter. You have to select the larger value and then you have to find out what is the diameter required D0 of the solid shaft. Then determine the required outer diameter D2 of the hollow shaft if the thickness T of the shaft is specified as 1/10 of the outer diameter. So in the first case, you have to find out what is the diameter required D0 in the case of solid shaft. And if you are using here the hollow shaft with the outer diameter equal to D2, inner diameter equal to D1, then we require here thickness T. And this thickness T is allowed is equal to 1/10 of the outer diameter. So we have T is equal to D2 by 10. So indirectly he has given us a relation between D2 and D1, that is the value of K is known. And in the third part we have to find out the ratio of the diameter, that is the ratio of D2, that is this value of D2 to the original diameter DO of a solid shaft, and the ratio of the weight of the hollow and the solid shaft. So one detailed numerical will take on the comparison of the solid and the hollow shaft. For both cases here, we have torque transmitted will be equal to 1200 Newton meter. Value of G is given as 78 gigapascal. Allowable shear is given as 40 megapascal for both solid and hollow, and theta by L is 0.75 degree per meter. So it will be equal to 0.75 degree per meter is 0.75 multiplied by pi by 180 is equal to 0.013 radian per meter. So that is another constraint for us. So first we will find out here the diameter for the solid shaft based on two constraints. One is the shear stress and second constraint is theta by L, and then we'll design the outer diameter D2 and the inner diameter D1 in the case of hollow shaft. So first we'll consider here a solid shaft and we'll find out the value of DO. So we have two constraints here. One is shear stress and the second is theta by L. So let's calculate here what is the diameter based on the shear stress allowable. For this one, for solid shaft, we have torque is given as equal to pi divided by 16 into d cube multiplied by allowable shear stress. Now this time I will going to use the data in SI unit only. So we have torque equal to 1200 equal to pi by 16 d cube. Shear stress will use in Pascal, that is 40 into 10 to the power 6. So value of diameter you will get will be in meter. You will get a diameter DO is equal to 0.0535 meter. For the same solid shaft, we have second constraint is theta by L. We know that theta, which is given as T multiplied by L divided by J divided by G. So we have theta by L will be equal to T divided by J divided by G. Theta by L is same as equal to 0.013. We'll continue here again the SI unit. We have torque is equal to 1200 divided by pi. 32 will shift in numerator. In denominator we have DO to the power 4 multiplied by value of G is 78, is giga is 10 to the power 9. So we'll get here the value of DO. SI unit we have used here, not conventional unit. This value is equal to 0.0588 will be meter. So one constraint says that our D0 will be 0.0535. Second constraint is giving you the diameter equal to 0.0588. In this case you have to select the larger diameter. So our one diameter is final, that is the value of D0 is final is 0.0588 meter. Same treatment we'll do for the hollow shaft. 0.0588 is same as equal to 58.8, that will be mm. So this diameter D0 is equal to 58.8 mm. So we have D0 is equal to 58.8. We have hollow shaft here with thickness equal to D2 by 10. So D1 will be equal to D0 minus 2 times of thickness, 1t here and 1t here. So we have D0 is equal to 2 times D2 by 10. We have D0 as it is minus 0.2 times D2, that will be equal to 0.8 times D2. Indirectly we have given the relation between D1 by D2 and we represent this value by K. So we have K is equal to 0.8. Now here we'll going to design the diameter D1 and D2 for hollow shaft. So first constraint we'll use the shear stress. For hollow shaft we have torque is equal to pi by 16 into outer diameter cube into 1 minus K to the power 4 multiplied by shear stress. Again we'll continue here SI unit. We have torque is equal to 1200 is equal to pi divided by 16 into D2 cube into 1 and K is equal to 0.8. So we have 0.8 to the power 4. Shear stress is same as equal to 40 megapascal is 40 into 10 to the power 6. So we'll get a diameter D2 in meter is close to 0.0637 meter. This is the one answer you obtained using the tau allowable. Our second constraint is theta by L equal to 0.013 radian per meter. So we have theta is equal to TL by Jg. So we rearrange this as theta by L equal to T upon Jg. J you have to use for hollow shaft. So in this case again we can calculate the value of D2. We have theta by L is equal to 0.013 is meter per radian. So again you have to use here the SI unit. Torque is same as equal to 1200 divided by pi. 32 will shift in numerator. We'll take out here DO to the power 4 common. So what is left is 1 minus DI to the power 4. That is 0.8. K value will come here. And then we have multiplied by value of G. G value is 78 gigapascal. So we have 78 into 10 to the power 9. So based on the second constraint, we get here diameter D0 is close to 0.0671 meter. So one value is 0.637, second value is 0.0671. So you have to select the larger diameter. So the larger diameter come out to be 67.1 mm. That is, this value is the larger. So 67.1 mm is the larger diameter that will finalize. And using this relation, we can calculate the value of D1 as 0.8 times of D2. 0.8 times of D2 is 0.8 times of 67.1 is 53.7. So we know the value of D1, which one is 53.7, and D0 equal to 67.1. All dimensions are finalized based on the two constraints. One is the shear stress and one is the twist per unit length. So for given constraint, we have diameter D0 come out to be 58.8, D1 for hollow is 53.7, and D2 equal to 67.1 mm. Now we will come to compare here weight. Now as far as the weight is considered, weight is given as a product of rho multiplied by G multiplied by area multiplied by length. Rho is same, G is same, length is same. Area is a product of pi into DO square upon pi into D2 square minus D1 square. So again the pi will get cancelled and it's simply the ratio of diameters. So since the weights of the shaft are proportional to their cross section area, pi will be get cancelled, and we have a weight of a hollow shaft to the weight of the solid shaft is D2 square minus D1 square by D0 square. In this case we have D2 equal to 67.1 square of it, D1 equal to 53.7 square of it, and for solid shaft this value is equal to 58.8 square of it. All this you will get this answer equal to 0.47. Means only 47% of the solid shaft will be the weight of the hollow shaft. So there is almost 53% reduction in the weight, and therefore hollow shaft is normally preferred in the case of power transmission for a large distance. So we have saving in weight will be equal to 1 minus 0.47 multiplied by 100. That is almost 53% is the saving in weight. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.